multiplication over the years. Okay, so here's a prototypical example. You have a matrix A and you want to compute A transpose X, let's say. And this matrix A is way too big. You cannot, let's say, do it on one computer, or even if you can, it's going to take too long. So what do? You typically try to distribute it. And I guess the so-called most straightforward way of doing it would be to, let's say, do just a block column decomposition of the matrix A. So you, let's say, chop it into 3 block columns. And so that when you're so the most straightforward way would be to, divide it into 3 block columns and give, let's say, 3 different worker nodes the task of computing those submatrix products, so that when all 3 are complete, then you can actually recover what you want. Now, the problem with this is, of course, that, let's say, for example, worker 1 is slow. Then what do? Your overall computation is limited by the speed of the slowest worker. So this is clearly not a very good situation to be in. And so, the term straggler refers to a slow worker or a failed worker in this talk. So what do you do to address this issue? And so you could do coded, let's say, matrix vector multiplication. And this was first suggested in this work by these list of people here in 2018. The conference version was a little bit earlier. So the idea here is now that you do not chop the matrix into 3 block columns, but instead you now chop it into 2 block columns. So these 2 blocks are now going to be a little bit bigger. Okay. And now what you do is you assign, again, 3 worker nodes to tasks. This one you give A0, this one you give A1. But now for the third one, you give A0 plus A1. So the overall computational cost on each individual worker has gone up. But now you see that, it's kind of straightforward to see that as long as any 2 workers are completing their tasks, you can actually recover what you want, which is A0 transpose X and A1 transpose X. So this is the very simple 2-minute introduction to coded multiplication, coded matrix vector multiplication. Now, this has a generalization. So the generalization to matrix multiplication maybe requires just maybe one more, I would say, kind of clever idea. And the idea is this now. So you're trying to calculate A transpose B, and you're again doing a block column decomposition of A and a block column decomposition of B. And so what you're really seeking to retrieve are these 4 submatrix products. Okay. And so the way to embed this into what I would call a coded matrix multiplication was first suggested by these group of people from USC and Mohammad Madali from Iran. And so the idea is this. So you create a what I would call a matrix polynomial in the A matrix and a matrix polynomial in the B matrix. And here you calculate A0 transpose plus A1 transpose, let's say Z, and B0 plus B1 times Z squared. So you need to choose this degree sequence a little bit carefully. And then you simply assign worker 0 to calculate, the product of these 2 matrices, worker 1 to calculate the product of these 2, and so on and so forth. Now, what's going on is that basically, if you think about this particular, let's say, worker number 2, it's actually calculating exactly this quantity here. I don't know where that came from. Went away. So what worker 2 is calculating is exactly this with I replaced by 3. Okay. So, and you can see that this is like a degree 3 polynomial in this with these kinds of coefficients, and the coefficients are what we're trying to retrieve. And so basically, if you receive evaluations from any 4 worker nodes, you will be able to decode because you'll be able to interpolate the polynomial. So that's the idea. Okay, so now this was after the original works in this area were published. The primary so-called what I would call the figure of merit for coded computation was this threshold, what I call the recovery threshold task. So the idea is this. So you're trying to do this distributed matrix computation problem. You are taking this and so giving different worker nodes these tasks. And what you want is that as long as any tau workers are able to complete their tasks, you should be able to recover your desired result. Okay. That's the computational threshold. And if you can see, like the matrix multiplication example that I gave you, essentially embeds this computation into a resolvent code. And the fact that it has the so-called optimal threshold roughly follows from the basic idea of the reason why we know that resolvent codes are endless. Okay. Now, what I want to do in this talk is to maybe focus on 3 aspects of coded computation, which I think are very important and have not been given as much importance or have not been investigated to the level as we can say thresholds have been investigated. And to do that, I'd like to draw your attention to, again, the same example that I showed you a couple of slides earlier. And let's suppose that, it's workers 1, 2, 3, 4, and 5, right? So if you see, if I were to divide it into a coding matrix and the unknowns, and these are the outputs, this is what it looks like. And so, if you take any n by n submatrix of an m by n Vandermonde matrix, this is going to be invertible. It's well known from the Vandermonde determinant identity. And so you are able to decode, and that is the guarantee that you get. However, the problem is this: Vandermonde matrices have very bad condition numbers. And what do I mean by the condition number? The condition number is just, for this purposes of this talk, is the ratio of the maximum singular value of the matrix to the minimum singular value of the matrix. So if I move around, you have to keep doing that, is it? So now, okay, so then I'll try not to move around. Okay. All right. So this is just the ratio of the maximum singular value of m to the minimum singular value of m. Okay, and it is in the numerical analysis literature, it's a well-known thumb rule that if you are trying to solve, let's say, y equal to m times x, so you know y and you're trying to retrieve x, then if m has a condition number of approximately 10 to the power of L, that is going to lead to about L bits of loss in numerical precision when you're trying to invert the system. So here's an example. So let's take, suppose that I have a degree 9 polynomial, so 10 unknowns, and I choose the evaluation point as integer and the evaluation point, no, so this is basically an interpolation at a certain signal to noise ratio. So what I'm doing here is basically taking a degree 9 polynomial, evaluating it at certain points. So the blue ones correspond to integers, the red one corresponds to evaluation points uniformly between -1 and 1, right? And I simply evaluate them, and I add a very little amount of noise, just to simulate this, and this is from SNR of 100. Okay. Even at that point, you have about 5% error. I just want to show you that this is very true. You can run this experiment in MATLAB. This is exactly what we did. Okay. The second thing I wanted to emphasize, the second motivation for this talk, is one about partial computation. So to do that, maybe let me just go back to this example one more time here. So you see here that so these matrices could be in general quite large. Even the submatrices could be very large, but they will still be something that these individual worker nodes can deal with. But so what I want to say is that if you go with this structure, either you get that a worker node has completed its job, or it has not completed its job. There's no intermediate state, so to say. Okay. So you're waiting for 4 workers to fully complete their job. But in reality, if you look at cloud platforms, there are cases when these worker nodes are actually somewhat slow, or they have different speeds. It's very difficult to quantify whether it is failed, or it is slow, or it is somewhere in an intermediate regime. So instead, what one could do is one could maybe subpacketize more and try to argue, for example, in this manner. So here's an example, again, 3 worker nodes, and we have chopped this matrix into 3 block columns. But now what we're doing is we're assigning 2 jobs to, or 2 tasks to each worker node. And it has the following property, that the way these tasks have been assigned, so the order of computation is from top to bottom. Worker node starts from here, starts going down, same thing with this. Now it has the following property, that, yes. The block diagram? Yes. Yes. So when you multiply, right, the coefficient of A1 transpose B1 would be 5 times y square, which would be 5 Yes. Yeah, that corresponds to the last theory. Thank you. So, yeah, so just coming back to this partial straggler situation. So imagine that, you have three worker nodes here. Let's say W2 is failed, W1 is slower than W0, and W0 is going at full rate. So in this situation, if I get two computations from W0, one computation from W1 and none from W2, I can still decode what I want. Okay, and this actually can be, you can actually verify that, for example, if all three operated at the same speed, then I would get A0, A1, and A2 from all three of them. And any combination, as long as it respects that sequential order, you can actually decode as long as any three block products are received. On the right, I have a different situation. So here, there's actually no coding, so there's just a block decomposition, and I'm putting copies of these stuff. And in this case, it can show that as long as any four tasks are complete that satisfy this sequential order, you'll be able to decode what you want. You may get like, two copies of a task that have already been completed, but. So what I want to emphasize is that there are situations in which there are, the worker nodes have different speeds. You have really no idea of what the different speeds are. So you want codes or schemes, distributed computation schemes that actually are able to exploit the partial work that is done by slower worker nodes. All right. So, and then the third motivation for this talk is sparse input matrices. Okay. So the vast majority of coded computation work so far does not consider the characteristics of these input matrices. Now, in many practical problems, especially let's say in computational fluid dynamics, you have scenarios where these input matrices A and B are very sparse. So like 99% of the entries could be zeros within them. And that's actually, very important. And I'll tell you why. So, if you take, for example, a situation where matrix A and B, let's say matrix A is sparse, and you do this kind of encoding, okay? So then the number of non-zero entries in this encoded matrix is about approximately 3 times of the number of non-zero entries in the original matrix A. So the computational time also goes up by that. Okay. So for instance, if it takes A transpose X about time alpha, and if it takes A0 transpose X, remember A0 transpose X is the first block column in the topic, it will take about alpha by 3. But then if you encode it like this and the density goes up 3 times, you are back to alpha. So your advantage when you're dealing with sparse matrices, your advantage of stopping the computation and poking it off to different worker nodes is essentially lost. So if your matrices are sparse, you have to be careful not to linearly combine too many of the block columns. Okay, so that's the third point. So that's the third motivation. So in particular, again, if you go back to this polynomial code, if a worker node stores 1 over Ka fraction of A and 1 over Kb fraction of P, then the polynomial code is going to be assigning a linear combination of Ka block columns of A and Kb block columns of B. So the overall cost is going to go up. Okay, so those are 3 motivations for this talk. And before I proceed, I want to talk about all these 3 things and in some level of detail. Before I go, are there any questions about the motivation? Yes. Yes. Right. So that is correct. I am only assuming worker faults here. But RS codes, yes, in theory, yes, you can get away with worker errors as well. But really, when you're working over the real field, those guarantees don't automatically transfer over. So what do you consider an error? I mean, I can take that discussion offline, but it's not so straightforward. I mean, let's like you say, you can recover so many number of errors over finite fields. The same guarantee does not hold in the real field. But yeah, that is a good point. In this talk, I'm only considering worker failures. either or a worker being slow. The worker does not add any adversarial noise or anything like that. So let me start by talking a little bit about numerical stability. So some related work in this area. So we have a work based on convolutional coding for distributed computation, where again we embed distributed matrix computations into the structure of a convolutional code, and and we provide computable upper bounds on the worst case condition numbers. So remember, what does the worst case condition number here mean? So we are assuming that we are getting the results back from a certain subset of worker node. That is going to correspond to a certain recovery matrix that you need to invert in order to determine what your intended product is. So when I talk about the worst case condition number, I'm talking about that. Right? And we also have some work using universally decodable codes. And there are alternative approaches. So Fahim and Kadambe in 2019, and I guess the journal paper appeared a little bit later. They used the so-called basis of orthogonal polynomials, and they showed an upper bound on the worst case condition number of the decoding matrix. This grows as order n to the power of 2 times of s, where s is the number of stragglers that you are resilient to, and n is the number of workers. And then you can use basically ideas from random coding. It's called random Patirao, which is a product code here, RKRP. And we use linear codes for the matrices. This is from Krishna Narayan's group at Texas A&M. Okay, so I guess this I've already talked about a little bit. So let me just say. So, when I said Vandermonde matrices are ill-conditioned, this can be quantified in a very clear manner. So let's take this, just to set the notation right here. If these are Vandermonde matrix, I'll call S0 to Sm-1 to be its parameter. So the first column here is, just the successive powers of S0, second column is successive powers of S1, so on and so forth. So Victor Pan in 2016, in a paper titled How Bad Are Vandermonde Matrices, actually showed that for real Vandermonde matrices, the condition number is actually exponential in M. So imagine an M by M Vandermonde matrix. The condition number explodes. Yeah. Now, the second thing that he considered was complex Vandermonde matrices. So your parameters S0 to Sm-1 are now complex numbers. And what he showed was this. So if you have complex Vandermonde matrices with parameters that are not on the unit circle, so either they are inside the unit circle or they're outside the unit circle, the condition number is still quite bad. The precise statement is somewhat technical. It depends on how many of those parameters are inside versus outside. But the net result that you can get out of this paper is that if you want Vandermonde matrices that are reasonably well conditioned, all parameters need to be on the unit circle. Okay. Yes. Yeah, so I'll come to that. Yes, so it is better to take numbers in the unit circle, but even it depends on, the parameter S. So FFT, yes, FFT has condition number 1. But the moment you start taking subsets of the FFT matrix or, subsets of the DFT matrix, the condition numbers will increase. That's the issue. Ratio of maximum to minimum singular value, right? So for a given matrix, the condition number is the ratio of the maximum singular value to the minimum singular value. And when I say worst case condition number, I mean worst case over all possible recovery matrices. Okay, so let's maybe hold that thought for a minute. I'll come back to it. So let's think about choosing parameters on the unit circle. Okay. So one easy way in which I could do this, right, is I could simply say worker node 1, you compute this, right? Worker node 2, instead of now using real evaluation points, I could simply choose the evaluation points to be complex numbers on the unit circle, magnitude 1. But the problem is this: if I did that, I am taking a real matrix vector multiplication problem and converting it into a complex matrix vector multiplication problem, and that's going to be costly. Complex multiplication is approximately, if you're multiplying 2 complex numbers, that's approximately 4 times as expensive as multiplying 2 real numbers. So you don't want to do that if you can afford it. And so if I were to kind of summarize this part of the talk in one line, what we are really wanting to say is that what we've done is we have a coded matrix computation scheme that has real computation, We do not have any complex arithmetic in it, but we are able to leverage the conditioning of van der Waals matrices that have parameters on the unit circle. So that's what our scheme does. So this is the informal statement of our theorem. It says that the worst case condition number is going to be upper bounded by n to the power of n minus tau. So n minus tau, remember, is the number of stragglers that I'm resilient to, number of failures I can deal with. So you can replace n minus tau, let's say, by s. So my worst case condition number is upper bounded by something like n to the power of s plus some constant. It's 5.5 in this case. Okay, so you talked about the discrete Fourier transform. So this is the DFT matrix. And it's well known that DFT matrix has condition number exactly 1. So it has perfect conditioning. Okay? Not in condition at all. But now, here is what happens. So if you take, let's say, omega q here is the qth root of unity. Okay. So my parameters of the van der Waals matrix, I'm choosing m parameters from the van der Waals matrix that are a subset of the qth roots of unity. Okay, that is listed here. And if I construct such a van der Waals matrix using an m by m van der Waals matrix with these parameters that are chosen as a subset of this guy, then the condition number of this guy is upper bounded by this quantity. So that's what we can show. So in other words, once you start choosing subsets, right, not the entire DFT matrix. So if you had a q by q DFT matrix here, then everything would be nice. You would get condition number 1. But now if you're looking at van der Waals matrices that are chosen from subsets of these guys, then the condition number does increase. Okay. So I want to say that this upper bound is polynomial if q minus m is a constant. Okay, so what is a rough sketch of how this goes? So our basic idea is this: we are going to use real matrices that have eigenvalues on the unit circle. So what are examples of these? So if you take a rotation matrix, which is this real matrix here, it has eigenvalues are e to the j theta and e to the minus j theta. J is the square root of -1. And if you take an L by L circle and permutation matrix, it also has eigenvalues omega L to the I. Okay. Again, omega sub L represents to the L roots of unity. Okay. So I can choose a circle and permutation and I can choose its power. And so that's what we do. So here's the encoding scheme, let's say, for the matrix A. So what we do is, this is a little bit of abuse of notation here, so I'll say what I mean by that. So we are going to, instead of splitting the matrix A into k blocks, I'm now going to split it into 2k block columns. And this matrix here, this is the identity of 2 by 2, identity 2 by 2. This is the rotation matrix of theta, size 2 by 2, and so on. So I choose now powers of rotation matrix. So what does this encoding mean in a specific case, right? So if you have 3 workers, what I'm going to be assigning to worker node 0 is going to be A00 plus A10 and A01 plus A11. So if I go back here, that corresponds to the first block column of this. If I look at worker node 1, this is going to be assignment of this one that corresponds to the second block column of this, and so on and so forth. And what I want to say is, now let's just try to understand what this scheme does for us. So let's just focus our attention on this toy example. Let's suppose that worker node 0 is failed, and I'm trying to decode from worker node 1 and worker node 2. So what ends up happening is the decoding amounts to, when I'm trying to understand what is the worst case condition number of this guy, the decoding amounts to, not the worst case, I'm sorry, the condition number of this particular recovery set, it amounts to understanding the condition number of this guy. Okay. And again, I can do a simple diagonalization of our theta, and I can show that, unitarily this is similar to a matrix that looks like this. So anything that doesn't appear here is a 0. And what ends up happening, therefore, is that we can show that, just by row column permutations, that this becomes, this can be decomposed as a block diagonal matrix, where each of those block matrices are now van der Waals matrices with parameters on the unit circle. So basically what that means is I have converted this, the question of condition number of my recovery matrix into the condition number of, again, random on matrices, but now the parameters are coming from. Okay. I won't discuss this in the interest of time. So this is, you can do something very similar, but now using circle implementation matrices, because those also have eigenvalues on the unit circle. And it has some nice properties like, fast encoding and decoding using the FFT. Okay. Now, I talked about the matrix vector case because it's somewhat simpler to understand, but a very similar idea applies to the matrix multiplication scenario as well. Okay. So once again, your encoding scheme goes exactly like choosing these powers of rotation matrices instead of just choosing powers of the complex parameters, and likewise for the encoding of the matrix B. And now the decodability and condition number looks something like, trying to understand what is the condition number of this matrix that I've given here. So these are canonical products. So if you do some more algebra with 3-row products and canonical products and so on and so forth, you can actually get a very similar result. Okay. All right. So here are some numerical experiments. So I'm computing A transpose B with A has a storage fraction of 1/4, B has a storage fraction of 1/7. So your optimal threshold is going to be 28. And so that's your threshold here. You have n equal to 31 workers. And if you look at this is, the y-axis here is log to the base 10 of the worst case condition number. So this is your polynomial code here. The polynomial code is sitting at about 10 to the power of 14. So that's actually very, very high in terms of worst case condition number. This is the technique of Fahim and Kadambe that I talked about, which is called when they are taking the orthogonal basis of polynomial. This is Chebyshev polynomial, and this is has a worst case about 5.8, 10 to the power of 5.8. The random 3-row product that is from Texas A&M, which is Narayan's group, that's about 4.75, and we are sitting at about 2.6 in terms of worst case condition number. So it's less than 1,000, for example. So for this method here is a randomized method. So it depends on what random parameters you store. So we pick the best after 200 independent random trials. And this is the result of actually decoding. So here what we are measuring is the Frobenius norm difference. I think that's actually a typo. Sorry, it's actually should be the Frobenius norm, not the L2 norm. So this is that ratio, and this is what we get with decoding. So basically, what I call this particular curve here that is sitting bang on top of the black curve, which is the rotation matrix embedding, is what you would get if you actually used complex arithmetic. If you use the evaluation points exactly as the points on the unit circle, this is what you would get, and this is exactly what we did. Now, here I want to say that polynomial code results are not actually plotted here because they are kind of really very, very high. The error is very, very high. Okay, so any questions about this? And we have many more details in the actual paper. Paper so much I had to reference for it, but I'm happy to share. It's all on my website. So any questions about this? All right. So the second thing I'd like to talk about in this talk, and I'm probably at the halfway point here, is about partial stragglers and the question of sparse input matrices. So let's try to kind of motivate this problem. So I want to understand, suppose that I don't do any coding. So I'll go back to the situation where I'm doing, let's say, matrix vector multiplication, and I'm chopping my matrix A into a certain number of block columns, but I only want to do an uncoded assignment. I don't want to actually do any encoding between the worker nodes. Then what do I do? So here's a kind of a design. So here's what I can do. So I have 5 worker nodes. I chop my matrix into 5 different parts. So A0 to A4. Okay. And I do this kind of cyclic assignment. So I do A0, A1, A2 in this, and then cyclically shift it to A1, A2, A3, A2, A3, A4, so on and so forth. Now, what we can show is that so delta here refers to the number of block columns I've chopped my matrix A into. And L here is the number of tasks I'm assigning to every worker. So here the storage capacity or the storage constraint is 3/5. And we can show that this matrix is that, I mean, this scheme is actually resilient to two stragglers. Okay. So the scheme is resilient to two stragglers. And what we can also show is that, so if you kind of just look at this particular pattern, so here's a pattern in which, W0 has done all its work, W1 has done all its work, W2 has only done 2, W3 has only done 1, and W4 has done none. So here's a scenario in which you can see clearly that this copy of A4 transpose X that we wanted to get is actually missing. So there's no way that the master node can be satisfied to actually calculate the product A transpose X. So to do this calculation, you can show that 9 blocks can be obtained without any copy of A4 transpose X. So we can say that, Q equal to 10, meaning that as long as you get any 10 worker computations that satisfy the sequential order, you'll actually be able to decode. Okay, so this shows that 9 at least is required. The fact that 10 is sufficient is natural byproduct of this argument. Now, what is interesting is that for the uncoded case, there's actually a matching lower bound, which I'm not actually talking about in this work, but it's there in the paper. You can show that, if you have uncoded assignment, then you have to have at least Q that is given by this particular expression, and actually that it actually matches that particular bound, Cyclic assignment. Okay, so what does this mean? This means, for example, that as long as you get any 10 answers back from your worker node, you don't care anything about what relative speeds they operate at, you're able to decode. Okay, so that's this idea, and now what we've done in our work, and again, I'm going to try to give a top level overview of what we've done. We have a class of schemes that actually are able to exploit partial strategy. So here's the so here is the problem setup. So we have n workers. Every worker has a storage fraction 1/k and 1/kb. So this is, by the way, the exact same setup that much of prior work is considered. And something happened. So here is what we have for our scheme. It has the optimal straggler resilience, which is to say that it is, so for this particular scenario, you can show that the optimal threshold is Ka times Kb. So you should be able to, the scheme should be able to recover from any Ka, Kb times evaluation. And we have that optimal straggler resilience. It leverages partial computations in the sense that the Q by delta value is low. And I'll say exactly, I'll give a more quantitative answer to it. And it's also suitable for cost-sensitive matrices because several of our assigned submatrices are going to be uncoded. Okay, so let me give an example. So here's the idea of how it goes. You take the matrix A and you partition it into delta A submatrices. Again, block columns. When I say submatrices, just block columns, which are given by the LCM. So least common multiple of the number of workers and K. Partition B in a similar manner into KB submatrices. Again, block columns. And here is what you do. You do a further class decomposition. You divide these submatrices into so many L classes, and each of these classes contains delta A by K. I mean, you divide them into these many classes. Each of these classes contains A submatrices. And here's the key idea. So we only code for the A submatrices within a class. So let me explain this by an example. And so maybe let me come back to this. So here's the idea. So let's take an example for 5 workers. Both gamma A and gamma B is 1/2. Okay. So we would set delta A to be 10 and delta B to be 2. And we have 5 different classes, and each of these classes will only contain 2 workers. For example, class 0 would contain A0 and A5 and so on and so forth. And here's what we do. We start assigning these classes in a cyclic fashion, in a very similar manner to what I had shown you earlier. But now I'm doing it for these so-called classes. And I will cyclically shift them, but now it's a block cyclic shift. Instead of shifting the next one being C1, I have shifted it by 2. So it goes to C2, C3, C4, and so on and so forth. And again, there's a block shift of 2 and a block shift of 3 and so on. The matrices for B are simply just random encoding with B. So I would choose some random coefficient R0 and R1, some random coefficient R2 and R3, so on. Okay. And now here is what we would do. The worker nodes in the top 4 are all going to be uncoded. For example, if I take C0, it could just be A0 or it could be A5. For C1, it could either be A1 or A6 and so on and so forth. Only this bottom layer is actually going to have any code. All the other, the first 4 in every worker node are going to be uncoded. Here's like a specific example. So I would place A0 to A3 uncoded, and then I would pick the coding across the 4th class. The 4th class contains A4 and A9, and then do this block shift. And again, this would be the 6th. This would be the 6th class, and so on and so forth. So it turns out that this particular scheme that I'm talking about here has certain properties. So this class C3, for example, appears in all the workers. So it appears in all the workers. For example, A3 appears here, A3 appears here, the coded plot appears here, and A8 and A8 appears here. Okay. And so this allows us to actually analyze the the Straggler resilient properties of this scheme in a very simple way. And what you can show for this particular example is that this particular scheme, as you might expect, is resilient to 1 straggler and Q is 23. So I want to emphasize what Q is equal to 23 means. You have delta A to be 10 and delta B to be 2. So you're required to actually recover 20 different submatrix products at the bare minimum. What this is saying is, as long as you get any 23 of these, you're able to actually decode. Okay, so let me say a little bit about what this assignment helps us to do. So if UI denotes the subset of worker nodes where AI appears in an uncoded block, and VI denotes the subset of worker nodes where AI appears in an uncoded block, then you can show that UI appears KB times. For example, AP appears here 2 times, right? And where it appears, in a coded fashion, it appears exactly once. And these are in distinct worker nodes. Okay. So, for example, A3 here appears in worker nodes 0 and 1, and the coded block appears in a substitute. So there's no overlap between these worker nodes. And the same thing holds, for example, for A9. It appears in a uncoded fashion in W3 and W4, and the coded block appears in a different. All right. And if you look at a class together, I won't go into the exact details of what this means, but if you look at a class together, the third class consists of A3 and A8. Together, this class appears in all the workers, right? So it appears in uncoded fashion here, and in the remaining one, it appears in a coded fashion. Okay, so what does this give me? So the idea is this, so we want to show that this scheme is resilient to n minus k times kb stragglers. So remember why this is important, because this is the optimal straggler resilience. You can't do any better than this. Okay, so the argument goes like this. If you assume that AI transpose Bj cannot be recovered, then this AI is going to belong to some particular class. And we know that this class has a particular size, and the number of unknowns corresponding to Cn is Ka times Kb. Okay. And using this previous lemma, we know that Cm appears in all the n workers. And then you apply a rank argument. You say that out of these n appearances of Cm, any K or Kb of them are enough to recover all the corresponding products. Now, this requires a slightly more careful argument, which I'm not doing right now, but that's the overall idea. It gives us a much more manageable system of equations that we can analyze for this class information. And when we said this, the scheme is optimal in terms of factorization. Now, I won't go into the details of the partial computation. We can actually, so remember what the skew parameter is. The skew parameter says that if you get these many tasks completed by the worker node, then you can definitely keep it. And we can actually do this calculation for this particular scheme. And I'll try to show this by some numerical examples. And this okay, so here is the idea. So if n and ka, for example, are co-prime, so then this ugly looking expression that you have here can be, simplified quite a bit more. And what it shows is that q by delta is approximately 1 plus s by n. Okay. So S here, remember, is the number of stragglers that you're resilient to. So typically you're not budgeting for too many stragglers. S is in 3, 4, 5. So this q by delta is actually a very small number, and just above 1. It has to be at least 1, it's just a little more than 1. And here's the idea, to give you an idea of why the argument works. Basically, this class C1 that I've shown here, not only does it appear in all the workers, it also appears in all the workers in different places. So, for example, at W3, it appears at the top, W0, it appears at the next one, W2 next, and then the fourth, and then the fifth. So, it appears at all possible locations. And this is true for any particular class that you pick. And that symmetry property has some advantages that you can exploit to actually do this calculation. Okay. All right, so let me then talk a little bit about sparsity. So why does this scheme preserve sparsity? The main reason is that, as you can see, there are 5 assignments here, but out of those, 4 of them are actually uncoded. So when you're doing this calculation, yes, there is coding in B, but A0 times this calculation is going to be cheaper than this coded matrix and this coded matrix. Okay, so you are saving on the encoding of A. So every worker has 4 uncoded and 1 coded submatrix from A. And this reduces the worker computation time significantly. I'll show some more numerical examples. So the overall storage fraction for A is 1 over Ka in our scheme, and the storage fraction for the coded A submatrix is actually 1 over Ka times S divided by N. Once again, I want to emphasize that S is actually a much smaller number compared to N. The fraction of coding in A is much less. And so here's a numerical experiment. So let's say you consider matrix multiplication with 24 workers, Ka to be 4 and Kb to be 5. So the threshold of the scheme is going to be 20. And let's consider matrices A and B, who, let's say, mu percent of NP. So here's an example. So let's say mu is 99%. So 99% of the NP. The polynomial code is going to be resilient to force value, but the worker computation time, the time it takes for you to calculate 2 of this, for a worker to compute its submatrix product, is going to be here 1.22 seconds. If you take ortho poly, it's actually almost the same. There's no reason to expect it to be different. It's going to be about 1.25. The random pair product code is going to be approximately 1.31, and so on. Our own method is actually a little bit reversed here. And these 3 schemes are all going to be following in the class of schemes that I've talked about so far. So this class-based scheme that I just discussed, that corresponds to actually this particular row, is sitting at 0.54 because of the advantage that most of the assignments are included. This particular row here, I have not actually discussed, but this is in one of our follow-up rows that I have discussed. Okay, so another experiment here. So remember, when we talk about our scheme, we have some uncoded matrices of A multiplying coded matrices of B, and then coded matrices of A multiplying coded matrices. So I'm just comparing now these 2 methods here. So clearly these are much higher. So these are all comparisons between our own work actually. So this is basically saying that if you pick this middle one that I've just discussed here, this is for uncoded A versus coded B, and coded A versus coded B, it's better compared to some of the previous work. Essentially, lower weights for coding of A and B make it faster. Now, here's an interesting plot, I would say. Let's talk about the overall computation time. So we consider again 24 worker nodes, let's say 2 98% class matrices. And we simulated this. We said that the slower workers have 1/5 the speed of other worker nodes. Okay. And so here is what happens. On the y-axis, I have the overall computation time, which is to say the overall time it takes for the master node to recover the product. So remember, the worker nodes are working. Some of them are slow, and the master node is waiting for the submatrix products to come in, and it can decode once it gets enough. Okay, so that's what we are checking for. And it is so imagine that there is no slow worker node. The polynomial code and orthopoly are still going to be somewhat expensive because they are using encoded matrices, and remember the input matrices are sparse, so they will be expensive to begin with. But nothing really changes as the number of slow worker nodes keeps increasing. This is the class-based scheme that I was discussing here, so it still remains very low until you hit the point which is the so-called threshold. So if you go beyond 4 slow worker nodes, it starts the polynomial code starts to take a major hit because it has to wait until at least 20 worker nodes give the result back. So at this point, when it hits 5 slow worker nodes, it has to wait for that at least one of the slow worker nodes to completely finish. That's why it kind of really bumps up here. But you see that for all our schemes, including the class-based scheme here, the decay is very, very gradual because you have this advantage that it can decode as long as it gets any few block products, regardless of the speed of the work. So this is a so-called completion plot, and we have many more such examples in the actual paper. And this is an example comparison of the Q by delta value. So, for example, here we have that at the bare minimum we need 120 block products, the worst case we need 139, and so on and so forth. And here this kappa worst corresponds to the worst case condition number. I should say that for the schemes that we have in this paper, we are choosing those these encoding coefficients at random. All these numbers are empirical numbers. These are actual outputs of numerical simulations. So we don't have actual theoretical upper bounds on the condition numbers, but these are outputs of actual experiments. Okay, and so again, but I just wanted to emphasize, kappa work is pretty bad for polynomial code. All right, so I think I kind of finished roughly on time. So I guess the whole point I want to make in this talk is that there are several relevant issues within coded computation. It's not just the computational threshold, which has been the most widely investigated. So what are those? At least according to this talk, we talked about numerical stability, partial stragglers, and sparse input matrices. Okay, and especially the first one, I think, is a very interesting topic or beast or whatever you want to call it, because I think we are very used to thinking in terms of to think about coding theory over finite fields. This issue of numerical stability is non-existent. It doesn't matter because it doesn't exist. But when you're talking about computation, it does exist, and it requires examining codes from that lens. Interesting, and has scope for more work. And as I said, our proposed approach can utilize partial stragglers because many of the assigned submatrices are uncoded, and this results to increase faster computation. So open questions, I guess, as I already said, numerical stability is an issue. And so investigating and tailoring schemes for this, I think, has several nice open problems. I'm happy to discuss more again. Among other important questions, I think, like as I emphasized, that many of the matrices that we encounter in practice are actually sparse, or heavily sparse. So it is quite important, I think, to consider coded computation schemes that are tailored for them. And also understanding the trade-off between the Straggler resilience metric, the Q by delta metric, and the weight of the linear combination. So we have some schemes and we have some, we're operating in a certain parameter range, but I don't think we have a complete understanding of that, or we're actually quite far from a complete understanding of that. So trying to get at better code constructions and better bounds and performance, I think, are open question. I'll stop here, and I'm happy to take more questions. Yeah, Aditya. I see. So I think that's a great question. I don't think I have a very satisfactory answer to that. But I will say that I have a maybe a slightly different, maybe not industry per se, but as I kept pressing on this talk a couple of times, right, I talked about computational fluid dynamics and the way that occurred in my view of this whole thing was that I had a colleague of mine in mechanical engineering who actually does these kinds of operations. They are dealing with matrices that are of the order of 10 million by 10 million, but very sparse, and they need to solve these differential equations that they essentially do by iterating matrix vector multiplies. And they do this all the time. And so he was actually very interested in my student's defense, and we started talking. And so his entire point was that, I'm not going to even consider this any further if you make this, if you do very dense encoding, because that just completely defeats the purpose of distributing it, because, it just becomes very expensive. And so they were very interested in this class of schemes that are, not doing very limited encoding, but still maintain the optimal threshold, which I think is very important. So at least they are interested. We are in the process of trying to see how to transfer this know-how in their setup. But as far as let's say, I don't know, by industry, if you mean like Amazon or Google and stuff, I'm not. But certainly CFD folks. Yes. So number one rule, so they do have techniques, right, for sparsity, especially in how they structure the computation. But the number one rule they want is they don't want to make the matrices more dense. So that's because that takes a direct hit. If you combine two matrices, you're taking factor of 2 hit in computation. You don't want to do that even. But they do have the issue, like for example, this colleague of mine, they I think done their simulations in Argonne National Lab, these huge clusters. They do have the issue that occasionally machines fail, and they are interested in having situations where it's really interfering.
Coded computation, are the stragglers all equal, or you tolerate any KS stragglers, or is there some priority or
no? So whatever I discussed is sort of any S straggler. There is no, I mean, it's not like this S stragglers will work, but this S stragglers will not work. Any S stragglers will work.
And is it possible to assign some weight so that you can schedule that worker nodes accordingly?
So is it possible to design schemes which are tailored towards like higher probability of failure for some workers versus others?
Failure or even straggling, like if it involves transferring data, and you are now your stragglers are also taking into account that delay in transferring data to the network.
I see. So okay, so the first answer is no, we do not consider that aspect, because so there is the overhead of creating those encoded matrices. So okay, so one thing is that the master node creates these encoded matrices, but that is only basically scalar operations and Gaussian operations. There's no these inner products that matrix multiplication involves. So in that sense, we neglect the computation that is being done by the master node, and then there is the aspect of distributing the matrices and then getting the answer back. So that is going to be there regardless of whatever scheme you apply in coded computation, as I can see. The issue of saying that, okay, so you have some a priori knowledge that some node is going to be more likely to fail versus some other node, that's certainly a very valid question. But so one of the things that we faced when we were starting to think about this Q by delta metric was, how do you really model that different nodes are operating at different speeds and so on and so forth. So this is like a completely agnostic to that. So as long as you get this much from this entire group as a whole, you can be done. But yes, I mean, if you have some prior distribution saying that, look, this node is likely to be more likely to fail versus some other node, you could try to optimize this for that. But none of this addresses that.
Any other question? Thank you, Dr. Ramamoorthy, for an interesting talk. As discussed before, we would like to remind the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. Thank you and have a great day.